Let's talk about the alternating series. And so what we need to decide is whether an alternating series converges or diverges, and there's really a three-pronged test for converging. So the first part is it actually has to be alternating. And that's a little weird considering we're using the alternating series test. Of course the series is alternating, but you do need to make sure it's alternating, and the question then becomes, well, what makes something alternate? So let's look at a couple examples of how we can make a series alternate. So let's go from 1 to infinity, and let's put a negative 1 to the n out in front of a normal series, right? We've looked at the series 1 over n squared, but this is the series negative 1 to the n, 1 over n squared. Now, what does this negative 1 to the n do? Well, it turns out that when n is odd, it's going to make this negative, and when n is even, negative 1 to some even power is just going to be a 1, and so it's going to make this positive. So this right here makes this series alternate. It happens to start out, this particular one has a negative, so it's going to go negative, positive, negative, positive. If I wanted to start out as positive, I could just put a plus 1 up there. And now I'm starting at this to be a power of 2 when n equals to 1, and then it's going to go positive, negative, positive, negative. It doesn't really matter. The fact that it's alternating, this is gonna make it alternate. Most of the time, that's all you're gonna see, right? This is some alternating series. This is some alternating series, negative 1 and 2 to the n over n plus 4. That's some other alternating series. Okay, so this is our typical one. Every now and then you're gonna see, you're going to see, I don't know what, negative 1 is like cosine of pi. You could see something like that. Cosine of pi to the n, which is just silly because cosine of pi is negative 1, so this is just another negative 1 to the n. Right, that's the alternating version of that. So I guess there are other ways to make things alternate, but pretty much you're going to see this negative 1 to the n out in front. How about something like this? How about negative 3 to the n over n squared? You want to remind yourself, this can start at whatever 1 to infinity, that this is the same thing as negative 1 to the n times 3 to the n all over n squared, right? Negative 3 to the n is negative 1 to the n times 3 to the n, which is this. So this negative here just makes it alternate. And we've seen alternating series before. We've had alternating geometric series, right? So this is our classic geometric series, n equals to 0 to infinity of 4 to the negative 1/2 to the n, right? We talked about alternating geometric series. This has an a value of 4 and an r value of negative 1/2, right? And so this was a equals to 4, r equals to negative 1/2, and we know that this particular series then was 4 minus 2 plus 1 minus 1/2 plus dot dot dot. It was alternating because r was negative. Again, we don't talk about these having a's and r's because they're not geometric. All of these are not geometric series. This is geometric, and again, we don't need to look at the alternating geometric series. We already know that for a geometric series, for it to converge, we need this to be true. So we already had alternating geometric, and we don't need any other tests for that. However, these tests we need a test for. So first part, we do need to identify that it is alternating. Part 2, we need to make sure that the terms decrease in absolute value, right? So the next term, the nth plus 1 term, is smaller. The nth plus 1 term is smaller than the nth term, right? So the terms are going down in value, and again, absolute value, because we don't care about the negative positive in this case. We're just looking at, are the terms going down in value, right? 2 is smaller than 4, 1 is smaller than 2, half is smaller than 1. And then the third part, we do need to make sure that the limit of a to the n as n goes to infinity is in fact 0. Okay, So what we can say for the alternating series, if it's alternating, if the terms decrease in absolute value, and the limit of a to the n is 0, then it converges, right? It converges if all of these things are true. It is alternating, they do decrease in absolute value, and the limit is 0, okay? So this is our alternating series test, and we use them on, of course, alternating series, okay? Again, if you look at the geometric series, it clearly passes this. It is alternating. The terms themselves do decrease in value, and the limit of this is 0. So if you applied the alternating series test to an alternating geometric, it would pass, of course, meaning it would converge. But again, geometric, we already knew how that operated. So let's look at alternating non-geometric cases. Okay, so the absolute home run poster child for this, meaning 90% of the time when you're looking at an AP test and you're looking at a question, you are looking at this guy. You are looking at -1 to the n of 1 over n from 1 to infinity. Okay, you're looking at that. Okay, that converges. Why? Well, we need to compare this. This versus this guy. Now again, we've gone at great lengths already in this unit to look at 1 over n. 1 over n diverges. It diverges based on the p-series test. It diverges on the integral test. We can compare it to something. So we know that this guy diverges, but this guy converges. Why does it converge? Well, because it converges based on the alternating series test. Does it alternate? Yes. Do the terms decrease in absolute value, right? You know, look at the terms. 1 over n. What happens to 1 over n? What's 1 over 1, 1 over 2, 1 over 3, 1 over 4? They are decreasing in value. And what is the limit of this as n goes to infinity? And the limit is 0. So this converges based on the alternating series test. However, this would diverge. So this passes the alternating series test. And not only does it pass, we need to talk about whether it's conditional or absolute. Okay, so an example of how an alternating series converges and the other one, the non-alternating version, diverges. So if it converges, we have to classify it as either, okay, so options. So if you have an alternating series, okay, it either converges or diverges. If it converges, it either has conditional convergence or it has absolute convergence. And it's really easy. Okay, so let's go back up to this guy. It's an alternating series. Its terms decrease in absolute value. Its limit is 0, so it converges, right? Our first choice. We know this converges, okay. Now, does it have conditional convergence or absolute convergence? Okay, so we already have decided that it converges. Now, if it's conditional convergence, meaning the only reason it converges is because it was alternating. So if we took away the alternating part, does this converge? Well, no. 1 over n diverges. So then this has conditional convergence. Okay, this is conditional converges. Okay, and let's look at a bunch of other examples and I can show you the difference. So what about alternating 1 over n squared? Okay, so it's an alternating series. So we go to the alternating series test. Is it alternating? Yes. Do the terms decrease in absolute value? Yes. Does this have a limit of 0? Yes. So this converges. So we already know it converges. Okay, does it have absolute convergence or conditional convergence? So if you were to take away the fact that the series was alternating, does the remaining series 1 over n squared converge all on its own, regardless of whether it was alternating or not? And you'd say yes, 1 over n converges so that the alternating version has absolute and absolutely converges. Okay, the alternating version of 1 over n is conditionally convergent. It converges only because it's alternating. The alternating 1 over n squared has absolute convergence because even if that series wasn't alternating, even if you got rid of that part, the remaining series would still converge, so it has absolute convergence. Okay, how about n equals to 1 to infinity of alternating 2n plus 1 over n plus 4. Okay, is it alternating? Yes. Do the terms go down in absolute value? Not even sure, but here's what I know for sure. This doesn't have a limit of 0, right? This has a limit equal to 2. The limit of this series as n goes to infinity is 2, which is not 0. So not only do we don't have to care about these two because this whole thing just diverges to begin with. Again, not all alternating series converge. This doesn't go to 0, so it doesn't pass the alternating series test, so it diverges. Okay? How about n equals to 1 to infinity of the alternating 1 over square root of n? Does it alternate? Yes. Do the terms decrease in absolute value? Yes. Does 1 over the square root of n go to 0 as n goes to infinity? Yes. Okay, so it converges. So we know it converges, and the question is, do we want to classify that as conditional or absolute? And so to do that, if it wasn't alternating, take away that, then no, it diverges. This would diverge based on the p-series test. So it does pass the alternating series test, so we know it is a converging alternating series, but it only is conditional. It's only convergent because of the fact that it was alternating. If you looked at the corresponding series that wasn't alternating, this guy diverges by the p-series test. Thus, we label this as conditional convergence. And you can go on and look at different ones. Again, this is going to be very similar to this. If you looked at the alternating, again, I can make this n plus 1. That doesn't really do anything. 1 over n cubed. It's alternating. Its terms decrease in absolute value. It goes to 0, so it converges. So we know it converges. And then the question is it conditional or absolute? Well, again, if you want to decide conditional or absolute, you want to decide this question, you need to look at the series, the same series, and just take away the alternating series part. Does that converge or diverge? Well, this series converges for the p-series, so this series has absolute. Absolutely converges. Again, it didn't even need to alternate. Remember, an alternating series is more likely to converge than something else, meaning it's easier to converge. Look, this diverges, this converges. Why? Because the alternating part makes this thing converge. Same thing here. This converges, this diverges, so it's conditional. This converges, but 1 over n squared would have converged, which is why this has absolute convergence. It didn't matter that it was alternating. It would have converged regardless, meaning it wasn't conditional. It has absolute. So if you're categorizing an alternating series, you have 3 choices. Conditional converges, absolute convergence, or diverge. First, just do the alternating series test and decide whether it converges or diverges, and then decide which type of convergence does it have. Does it have conditional convergence or absolute convergence? Okay. So I just want to throw out one more small point about why it's easier for an alternating series to converge, and I want to talk about it being a self-kind of correcting system here. If you think about an alternating series, so let's look at a geometric example. So we'll look at one series, 4 plus 2 plus 1 plus a half plus a fourth plus dot 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 dot. Okay? And if you look at a graph of the sum. These are the partial sums as a function of n, and this is n. Okay, if I look when the 0th partial sum, meaning I started at 4, that'd be 4. And then if I let n equal to 1, meaning I'm looking at the first partial sum, the first two terms, I get 6. So instead of 4, I'm up to 6 now. And then if I use 3, I go up to 7, 7.5, 7.75, and so on. And you can look at the partial sums are approaching the real sum. Because if I look at the limit of the partial sums as n goes to infinity, I'm actually looking at the whole sum. I would get that that's 8, because I know the sum of a geometric series is a over r, and I get 8. Okay, let's look at the alternating version of the same thing though. 4 minus 2 plus 1 minus a half plus a fourth minus an 8 plus dot 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 dot. But now it's this self-correcting system. So the first one is at 4, but then the next one is at 2. Because I get 4 minus 2 is 2. And then I get 4 minus 2 plus 1, which is 3. So I'm too big, too small, bigger, but now smaller by a half. So 4 to 2 to 3 to 2.5 to 2.75 to back. So in this case, I'm doing one of these. My bottom layers are kind of converging that way, and then my top is going this way, and I'm getting to that perfect value, which is the actual sum. But you see how each sum I get better and better. So I go up to 4 and then down. This is an upper bound and this is a lower bound, right? But the real sum has to be somewhere between the original 4 and the next one of 2. Because my next guess is if I use 3 terms, it's better. It's the 3. And then if I use 4 terms, then I get 2.5, which the sum has to be between them, because the next thing I'm going to do is I'm going to add. So now I know the sum is between 2.75 and 2.5. And so I keep getting better and better. The more of these I use, obviously the closer I get to the real sum, and that's true up here. But the alternating goes boom, 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 and you're bouncing back and forth between the real value, which makes it easier to converge. Where here you're always adding, and you're getting higher. And I'm not saying all alternating series do this. I'm just trying to make a point numerically that it's an alternating series. It's easier to pass that test. Remember, the 3 prongs to the test are alternate, decrease in value, go to 0. Well, lots of alternating series do that, which is why a lot of alternating series converge.